It's always more interesting when you go deep down a rabbit hole, find out the truth about things, and then bring that back rather than being very visible but saying a whole lot of nothing. Accessing and updating state is the largest driver of performance issues in blockchains today.
Can you briefly describe the architecture of NOMT?
Think 10 times as many blocks in the same amount of time. Updating the tree and proving it 7 to 8 times improvement. Proof sizes is also reduced close to 50%.
There's this, I don't know what he's calling it, jam.
Yeah,
this little idea about
this,
jam.
This jam thing.
Yeah. What are your thoughts on jam?
The launch team wishes you good luck and Godspeed.
Space Monkeys blasting off with Robert Habermeier, a founding engineer of Polkadot, and we're here together today to talk about state, splash around a little bit, and see what we get up to. Rob, thanks for coming on the show. Nice to have you back.
Good to be here. Always better to do it in a pool too.
Yeah, it's good. We did it in like an office last time, and this is a little bit more comfortable, I think.
More relaxed for sure.
You kind of been out of the public eye, out of the picture for a little bit there. Figured you were off working on something that interested you. And it turns out you have. And it's all around this concept of state.
Sure. Yeah, I'm doing a big project around state right now. It's always more interesting when you go deep down a rabbit hole and find out the truth about things and then bring that back rather than, being very visible but saying a whole lot of nothing. So
yeah.
I think I have some things to say today.
Well, welcome back, and nice to have you in the new founder haircut and the new founder style.
For some reason, we all independently decided to buzz our hair within a couple months of each other. Like
sure.
I did it in like late November, early December, and I think Gav followed up with that like in January or February.
Nice. Well, the winter was long, and now it's time to come out.
Exactly. We're ready to swim. We're ready to dive into the code and
nice.
Make everything more streamlined.
So let's start with state, right? Because I think it's a word that we hear bandied around quite a lot, but maybe a lot of us don't really get the nuance of what we're talking about. When a blockchain engineer talks about state, what's he speaking to?
Well, state is the truth, the current truth of the blockchain. So it's, all of the balances of all of the accounts, all of the state and all of the smart contracts. Let's say which tokens exist, which swaps exist, which pools exist, whatever it may be. This is all stored as what we call state. And the blocks contain transactions that update this state. But the state is the thing that we agree upon, as well as the order of the transactions which modifies it.
Are the transactions that happened in the past part of the state?
It depends how you look at it. So, I think from, one definition of state, like the state of the chain, you could say that includes everything that's happened up until now. But what we're specifically referring to when we say state, and this is the industry standard connotation of the term, is like current state, the state as of the most recent block.
Yeah. The state of the blockchain.
The state of the blockchain.
I love
it. That's right.
Okay, nice. So, thorny issue. It gets in the way of a lot of performance. What can you say about how state contributes to bottlenecks in blockchain performance?
Well, accessing and updating state is the largest driver of performance issues in blockchains today.
Okay.
And the reason for that is, let's say you're doing a transaction. I'm transferring some tokens from myself to you. Every node that executes that transaction has to load my balance and your balance from the state, which is usually kept on the disk of the node, right? Like you have your CPU, you have your RAM. RAM is for like temporary stuff. But the state is permanent, right? Like it needs to be kept on a hard drive or an SSD.
Okay.
And accessing an SSD and loading those bits of state takes about 100 to 1,000 times as long as, say, reading that out of RAM or reading it even over the network in the same data center. And most of the time that blockchain nodes spend executing transactions is like waiting to load state for a long time, doing a tiny bit of computation, and then waiting to load another piece of state, and then doing a tiny bit of computation.
Okay, and the result of that tiny bit of computation after loading all that state is the new state.
Exactly.
Okay,
It results in changes to state based on user-provided code, smart contracts.
In a network like Polkadot, because you spoke about the node there, the state is stored in these nodes. But not every node has all of the state, or it does?
That's what we refer to as a full node, a
full
node
node.
that stores all of the state. But in the Polkadot paradigm, every parachain has its own state. The relay chain has its own state, and every parachain has its own state. There's no node that stores all of the state for all of the parachains, but a full node for some parachain or a full node of the relay chain would store all of the state for that chain.
But the relay chain, the core Polkadot chain, the state of that chain contains the state of all the parachains.
It contains commitments to that state.
Ooh, what do you mean? What do you mean?
When we say a commitment, we are referring to a really small piece of data that actually is a fingerprint of the entire current state of the parachain.
Oh.
And that's done using a Merkle tree,
Okay.
which is the data structure that most blockchains, but not all, keep their blockchain's state data within. So Polkadot keeps essentially a fingerprint of all of the parachain's current state, but not the whole thing.
Can you derive the whole thing from that fingerprint?
That's exactly why we use Merkle trees.
Okay, so let's talk about what Merkle trees are. I think Merkle trees are some form of compression. Is that accurate?
It's a kind of compression. You can get a commitment to the whole state in a very small value, and then somebody using that value, that's like what we call the root of the state tree,
Sure.
is able to prove to you anything that's in that state right now. So for example, and this is actually exactly what light clients do, or like properly written light clients. Your light client doesn't keep the whole state, but it can keep track of the current root of the state tree. And then somebody can go to you and say, I'm going to prove to you that your account balance is this based on the state root that you have. And the purpose of Merkle trees is exactly this efficient inspection without having all of the data.
Gotcha. You said some blockchains don't use Merkle trees. Can you speak to that real quick?
Sure.
Do we know any of them?
The biggest ones, you may have heard of it. It's Bitcoin.
Yeah. Okay.
It was a long contentious topic in Bitcoin. So Bitcoin runs off of what are known as UTXOs, or unspent transaction outputs. It's a fancy term for saying like potential transactions, or like the inputs to transactions that could happen in the future.
Sure.
Bitcoin blocks don't contain any commitment to the set of all pending transactions that could happen, or UTXOs as they're known.
Okay.
Instead, a full node just keeps their own list of it, and if the nodes are coded well, all of the full nodes have the same list. But there's no way to prove to somebody who's not running a full node that a particular UTXO exists or doesn't exist.
Is there any advantage to not using Merkle trees, or is that just because it was early days and this was the way we did it?
The main advantage is speed, and this would actually bring us to the second notable example of a blockchain that doesn't Merkleize state, which is Solana.
Oh.
You can imagine just keeping a list or some kind of database of all of the state in a flat format, right? Keys, lookup to value is much cheaper storage-wise, computation-wise, data-wise than just, trying to put that all into this authenticated tree structure.
Right.
So Solana forgoes that altogether.
I see.
Yeah.
Okay, because a Merkle tree, like each part of the tree is like a hash of what came below it. Is that
That's
how it
right.
is?
Yeah.
So to work backwards, you'd have to...
You'd rehash.
Okay.
I mean, to dive into that, you've got this like tree data structure.
Yeah.
And, a tree is based off of nodes that have nodes below them.
Yeah.
And so on. And all of the data kind of lives at the bottom of the tree. For some reason in computer science, we always draw trees upside down,
Okay.
Don't ask me. I didn't invent it.
Kind of dark, okay.
But the root's at the top and the leaves are at the bottom. But
Okay.
all of the data, essentially like, my account address to my account balance lives in a leaf. And so imagine this changes. The way a Merkle tree works is that every node is based off of the hashes of the nodes below it. So we're trying to go from like this leaf all the way down here to the node above it. So we hash, then we go up here, we hash the nodes below it, then we hash all the way up to the root. So it's a lot of computation. It's also, you have to, when you're doing a query into this tree, you have to fetch all of those nodes as well and inspect them and so on.
So does this relate to what you were saying earlier about, waiting for the state? Is that what's happening when we're waiting for the state?
So in some systems, yes. And actually in Substrate, as currently, that's exactly what is happening.
I see.
But the general approach that's being adopted now for performance, so this is what's being done in Geth and Reth, in Penumbra, I think even in Cosmos SDK, is you keep two copies of the state. You keep one that's a flat store that you can query really quickly.
Oh, yeah.
And you keep a Merkleized version of it also.
Okay.
So the idea is that when you're building a block or executing a block, you're not doing all of this tree traversal where you like have to load a node and then go to the disk and load another node and then go to the disk and load another node. Rather, you are able to just make a quick query and then do all of that processing at the end once you've already made sure that the transactions are correct.
Okay, so I want to know then, Solana decided to do, what did you call it, flat?
A flat, yeah. Flat storage.
Flat storage of all the states in the past.
Yeah.
What's the downside to that? Why doesn't everybody do that?
Well, it doesn't allow support for light clients. And in particular, bridges. So when I say light clients, I could refer to, a mobile user, but I think more importantly is trustless blockchain bridges. The idea that somebody could even get a consensus proof of a Solana header, and even with that consensus proof, they wouldn't be able to prove that your balance was this on the Solana network.
I see.
Yeah.
I guess you'd have to be a full node of this entire...
Right.
Is that right?
That's exactly right.
To do it yourself.
Yes.
And that's why light clients can't do it.
That's why light clients can't do it.
A light
because
client isn't a full node.
You couldn't write a smart contract on Ethereum or on Moonbeam that is a full node of Solana.
Okay.
It would be computationally intractable.
And the reason we don't just always use full nodes is because...
There's one key reason, which is it's when you're resource constrained. Like if you want to run a node on your phone, most of the world is mobile.
Right.
You can't run a full node on there. It would use up all your data. It would use up all of your battery all of the time. So a light client is the best for that. And also for these smart contract cases, like blockchain bridges are a kind of light client. They would run on pretty much the exact same technology as a light client on your mobile phone with some slight changes.
So back on Polkadot, this, I think, as you've already described, is a bit of a bottleneck in the performance of Polkadot. Why is it important to optimize these Merkle trees or the storage of the state?
There are two key reasons. So one is speed, building blocks faster.
Yeah.
The more blocks you can build, the more transactions you can do. And right now, the bottleneck on Polkadot scaling, I'd say, is the speed at which collator nodes can build blocks.
Okay.
Especially once you get into large databases with tens of millions or billions of accounts or state items, if we want to go globally scalable with this.
Yeah, right.
That's extremely important. So building blocks on Substrate right now is pretty slow. It could be much faster. So this is a very important bottleneck that I see the need to alleviate. And the second reason is related to that. It's about proof sizes. So when we're talking about, you have a state root and somebody wants to prove to you that your balance is this. When a parachain block is being shipped off to Polkadot validators, it basically comes with a big Merkle proof that proves all of the data that was accessed during that block.
Okay.
And we're kind of data constrained there. Every parachain block can only come with 5 megabytes of data.
Okay.
Let's take an example. If you take the current Substrate tree database and you create a version of that which has 10 million accounts, and you do 25,000 transfers. So you pick 25,000 accounts, you have them send to 25,000 random accounts. The proof size to fetch all of those data and send that to the Polkadot network for validators to check is about 29 megabytes.
Okay.
So this is only with a couple tens of millions of accounts. And this may be at like 20 million account, but it's certainly less than 100 million, right? So we're not talking about anything close to world scale right now.
Right.
So the reality is that if you wanted to scale up a parachain right now to something truly world scale, the bottleneck would be the state data as well as how fast your collators can build blocks.
Gotcha. To your knowledge, are there any blockchain architectures today that could scale to the world without sacrificing decentralization or security?
Well, it depends how many transactions the world is doing. There are different approaches.
Yeah.
Most of them involve compromising on centralization to some extent, at least in terms of liveness, if not safety. Liveness being the ability of that chain to continue in the face of faults, right? Like if you have one node that makes all of the transactions or makes all of the blocks, if that node goes down, you're kind of in trouble. But no transactions would be bad. So I think that's the trade-off that a lot of like hyper-scalable systems are going for right now.
Okay.
But, optimization of software and engineering projects is often, it's a battle of inches. It's not as if there's one great thing that's going to fix everything. It's more of like you improve things 10% here, 10% there, 10% there.
Sure.
And you do that over the course of many years, and all of a sudden you have something that's very battle tested and refined and can serve the needs of the world.
You've been throwing around some numbers lately, some percentages in relation to this project that you just came out with, NOMT, N-O-M-T, which stands for?
The nearly optimal Merkle tree.
And this was done in association with Sovereign Labs.
That's right.
Yeah, which isn't a Polkadot project.
Not a Polkadot
They're
project.
building an SDK for rollups, general rollups.
Yep.
What's the source of truth for those rollups? Is it meant to be Ethereum or?
No, they're actually very cross ecosystem.
Yeah.
So like there are Bitcoin rollups. I believe Citria is one of the bigger names. They're going to use Sovereign SDK. That
Sweet.
I'm fairly certain of that, but fact check me. They came out a bit of the Celestia ecosystem, but they're also looking at Ethereum. They're really just interested in creating a lot of rollups. So Sovereign SDK, Preston Evans from the Sovereign SDK, came up with the outline of the software architecture that we're using for this database. I mean, when you get into actually engineering something, millions of hairy details emerge, but the core ideas that make our state database very fast for updating and proving come originally from Preston, and they're supporting the project financially. However, our goal with NOMT is for it to be a driver of performance across the entire industry.
Anybody who uses Merkle Trees.
Anybody who uses Merkle Trees.
That's fantastic. Yes. Can you briefly describe the architecture of NOMT?
Sure. The idea is to take advantage of how SSDs, solid state drives, work today. What kinds of things are they good at? What are their best access patterns? And it turns out that SSDs are really good at storing and fetching data randomly. As long as you don't care too much about access latency, if that makes sense, how long you're waiting for any particular request, but the throughput can be high.
I see.
And as long as that data is in fairly large size. So if you're fetching like a byte here and there, it's very inefficient. But the truth about SSDs is that if you want to fetch like even a single byte, you're always fetching what we call a page, which is just a bundle of 4,096 bytes usually. It can vary from device to device. So what we do is we organize the tree into pages of 4,096 or just shy of 4,096 nodes at a time. And we do it in such a way that whenever we need to load a particular part of the tree, we can send out all of those requests at once to the SSD. Imagine you've got a big file, because that's actually what our database is, more or less. It's just a big file that we happen to be reading like random parts out of.
And so it's the ability to go in and find that specific piece of information.
Nice. And fetch lots of those in parallel very quickly. I mean, we're looking at a factor of 10 times improvement just on reading state compared to Substrate, compared to the existing Sovereign database.
Wow.
This is due to the flat store as well as some other optimizations we've done. So what this means is that you could build blocks about 10 times faster, think 10 times as many blocks in the same amount of time, potentially. If you have 10 seconds to build a block and it takes you 10 seconds, you build one. If it takes you 1 second, you build 10.
No, I mean, I get the simple math. I'm just kind of blown away. Go ahead.
It's a big leap. And then in terms of actually updating the tree and proving it, it's about a 7 to 8 times improvement over the current Substrate and Sovereign SDK trees. So it's also very fast in that respect. And in terms of proof sizes, the amount of data that it takes to prove a block of this kind to a zero-knowledge circuit or to a Polkadot validator is also reduced substantially, close to 50% in some cases.
Okay, you did lose me a little bit there. Why is that reduced? Why is the proof reduced?
That's because we use what's known as a binary tree rather than a hexary tree. Sounds daunting, probably.
Right, I'm with you.
For the folks at home, it means that a node in the tree can have 2 children, but in a hexary tree, it means that a node can have anywhere between 0 and 16 children. So imagine you're trying to prove a piece of data that's down some path in the tree. You might need to load a node that has 16 children and you only care about one of them and the other 15 are useless. So it's junk data. It's junk data that gets it fills up the proof that you don't need.
That's awesome.
And the original problem that hexary trees were trying to solve was exactly this thing about fetching larger pieces of data all at once, but it doesn't solve it as well as essentially using a binary tree and just organizing the nodes better.
Great stuff.
Yep.
Okay, real quick, I want to know, as far as on the node side, the hardware requirements, does this change what a node would have to look like?
Our goal is to run on like normal consumer hardware.
Yeah.
Like I run on my desktop PC at home. Pet mostly develops from a MacBook.
Yeah.
We're targeting Linux for node operators. That's the case, but we also want it to work on Mac.
Cool.
Linux is going to be, our real performance target. Nobody's running like production nodes on a Mac, but people do develop on Macs.
Yep.
And not many people develop on Windows, so that's out of sight.
Yeah.
You don't need a super fast CPU. You don't need a fantastic SSD. Like it will just work. However, once a blockchain gets into doing tens of thousands of transactions per second, your 10-year-old laptop might get overwhelmed. Even your 2-year-old laptop might get overwhelmed.
Okay.
But that depends on essentially how far that particular blockchain scales.
So Sovereign Labs funded this development. This development is going to help anybody, any blockchain that uses Merkle Trees.
Yep.
You did mention Substrate in there, so is there an intention to bring this over to Polkadot?
Yeah, absolutely. I actually wrote a sketch of how the architecture created by Sovereign could be adapted to Polkadot and Substrate in a post on my blog, rob.tech, in February. Okay. So, if you want to see some diagrams on kind of what that would look like, what kind of additional work needs to be done, and what are the motivations for that, it boils down to what we're currently building doesn't support iteration over the state, essentially. Like, say, go through all keys from this palette because we're doing a storage migration, which is a very common use case in Substrate.
Okay.
So to make it support iterability, there would have to be additional changes, and we are looking to build that into Substrate as well.
How does this fit into the roadmap of asynchronous backing, elastic scaling, things like we've been talking about with this Polkadot 2.0 idea?
Yeah.
How does this fit in with all that?
It's drawn off of dynamic scaling from the cloud, right?
Sure.
Use the block space that you need when you need it.
Yeah.
One side of that is agile core time, which is, if you only need a little bit of block space. But as we've seen, the largest use cases on Polkadot are going to use a lot of block space.
Yeah.
And elastic scaling is about making sure that they can get what they need. Now, I'm no longer at Parity. I'm not on the team working on elastic scaling. However, this work is actually complementary to elastic scaling in the sense that it could allow parachains to use way more cores than I think the folks at Parity or in the community have kind of expected so far out of elastic scaling. So most people, when they think about elastic scaling, are like, oh, a parachain is going to be able to use 2 or 3 cores.
Okay.
I think we should aim for more like 10 or 15 or more at a time, wherever possible.
Okay, and can you relate the bottleneck you were talking about earlier to this situation of elastic scaling?
Accessing state faster means creating blocks faster, means using more cores.
Okay.
You need a node that's going to build all of this stuff that's going to be put onto all of those cores.
Yeah.
And, you're using 10 cores every 6 seconds. Well, you need to create 10 blocks every 6 seconds. And, accessing state faster is one of the ways that you do that.
I see.
But cores are also bounded by the amount of data that they can receive. So having smaller proofs means that you need fewer cores. You could actually imagine once a state gets large enough that you need more cores simply because you have too much data, not because you're doing too much computation.
Yes, okay.
So cutting the data sizes down by half means that you also need to use fewer cores.
Okay, that's awesome. Are you thinking about anything after elastic scaling? There's this, I don't know what he's calling it, jam or something like that.
Yeah,
this little
I heard
idea about
this,
jam.
This jam thing.
Yeah. What are your thoughts on jam?
I was involved in a lot of the early design discussions around jam. I'm not currently working on it. I know Gavin's working with a team of developers to ship it. Jam takes a lot of steps that I think are really important. One, fragmentation. There's this quote, and I'm going to absolutely butcher it.
Sure.
But from The Death and Life of Great American Cities, and it's not, which was written by an urban planner by the name of Jane Jacobs. And she quoted a professor saying something along the lines of decentralization is a sign of decay when it does not emerge from centripetal forces. And what that essentially means is that, you need an engine room and you need to scale out of that engine room. And I think, one of the problems we're facing in Polkadot is too much fragmentation too early. And when I say decentralization here, I don't mean, resilience. I don't mean that there should be single points of failure, but rather that sort of the urban planning of Polkadot has been too decentralized. We're like, there's going to be a business district that people are going to go to for business. There's going to be a residential district.
It really has felt like an empty football stadium a little bit, like there's like a few things around here, but it's not the crowd.
Exactly.
So the energy.
The main direction that I see Gavin going with Jam is create that thriving neighborhood and remove some of the opinions around how Polkadot cores should be used to allow that to come to fruition. It's a long project. There's still a lot of question marks hanging over it. But that's the core idea, which I think is correctly motivated.
Nice. His ability to bring things together when they need to be brought together and let them be parallelized when they want to be.
That's right. And not create a protocol that guides people into particular patterns of usage, if that makes sense. We're sort of, the parachain system has funneled people into their own enclaves.
Yeah.
And that has been counterproductive in a few ways. So I think the goal of Jam to change that makes a lot of sense.
Maybe one of the primary ways it's been counterproductive is it's difficult to share state until you get to the core relay chain, right? And then maybe it's too late to do what you wanted to do.
Indeed. I really hope that our work on state will also have implications for Jam, that it will be adopted by Jam to build, whatever people want to build on Jam. And that's the nice thing about building the state database is that everybody can use it. It's going to increase performance across the entire industry for anybody who does decide to adopt it.
Yeah.
So it's pretty much a win-win.
Any aspects of Jam that are still big question marks for you, or perhaps you feel there are problems that Jam doesn't address yet, as far as you know?
Well, Jam is mostly about, and approaching this from a technical perspective, because I think there are also a lot of perspectives that are very important to the community about, what's going to happen to the existing parachain system, what are the migration paths for teams, stuff like that, which I know were brought up on previous Q&As, and I think are best answered by people working on Jam themselves.
Yeah.
But when I look at the Jam proposal and spec, the big open question is, where are these work packages going to come from?
Right.
Who's going to build them? And how do you make sure that when you've got large amounts of work packages coming to Jam validators, which are split up into many different groups, how do you make sure that, they land on chain, that you get ordering of them, and that you don't get gaps and things like that?
Yeah.
So the sequencing question, I think, is very important. Yeah.
I guess you'll need some high-powered sequencers.
I think so. But, the question is the technology going to be low risk enough for the large entities that could build high-powered sequencers? For example, like what Jump is doing with FireDancer. Are the barriers to entry for them to create that sequencer low enough for them to do it?
Yeah. This guy's actually going to get in a...
Bon voyage.
Yeah, that's a big question mark for me as well. And I don't think it's been spoken to. Or maybe the question hasn't been asked. I'm not sure. Have you asked the question?
Yeah, I know Gavin is thinking about sequencers, but not as something for 1.0 of Jam, like a first version of Jam.
Okay.
But I do know that he's aware of this concern and wants to address it or find suitable abstractions for the community to address it in later versions.
Yeah, well, it's an interesting time for you, Rob, to be, you say you're not working on the core Jam, the core Jam project. How would you define your goals with blockchain technology these days?
Well, I think the same as ever. It's I'm highly motivated by building code that lots and lots of people are going to use. I'm very motivated by true open source approaches, where code is released under free, permissionless licenses that anybody can adopt. I got into the blockchain space through open source, and I really like those principles. My goals with Polkadot, I'm going to continue sticking around in Polkadot, participating in governance, discussing things on Twitter, and providing some commentary and advice to people who are around. But right now, I am not full time on like Polkadot core stuff.
Yeah.
However, I have truly no intentions of leaving this wonderful community.
That's great. What is the Polkadot project you are most excited about right now?
I think Hyperbridge is the most exciting, and I'm actually not even an investor in Hyperbridge. But I think it's really interesting from the perspective of here's an application that could use all the cores. And here's an application that's going to bend those expectations of what Polkadot could be used for. You know, it's building a parachain that pretends to be a parachain, which I find incredibly fascinating, that it actually shows that you can do some jam-like things on Polkadot 1.0 already today.
There you go.
And it also casts, I think, Polkadot as an opportunity to sell the top of ZK and buy the bottom of crypto economic compute.
Nice.
Where those two things can be interchangeable. And I've written a little bit about my opinions on like the market structure for ZK versus crypto economic, if you want to get my deeper thoughts on, you know, where that.
Yeah, I remember we covered it a few months ago.
Okay, well, that's cool.
Yeah.
Good. When we're discussing ZK versus crypto economics here, these are different technologies, but what people use them for is often the same thing, which is proving that a block or a transaction or some computation is done correctly. And these have different properties. So, for example, in ZK, it's very computationally expensive. It often takes a long time. There's a lot of very complex mathematics involved, which may be error prone, like we'll see. I think there have been some issues with implementations. But speaking strictly about economics, you're going to pay more, wait longer, but if there's a lot of demand, the price doesn't change. Whereas in a crypto economic setting, everybody's kind of competing over the same 1,000 Polkadot validators, for example, to check their transactions. So you get fee spikes.
Sure.
So the cost is lower, but I would argue and have argued that ZK imposes a kind of cost or price ceiling on fees in a crypto economic setting. But this isn't necessarily a bad thing. I think it kind of bounds Polkadot's maximum potential profit or whatever. But crypto economic coprocessors can actually operate quite profitably, because if ZK is 10 times more expensive, that means that crypto economic coprocessors could operate at a 90% profit margin.
Yeah, it's awesome.
Right? Before people would start switching over to ZK from a price perspective, from that pressure.
Yeah. It'll be interesting to see when ZK comes to Polkadot and how it does, if it does. But I'm pretty satisfied with
I think it's inevitable
right
because
now,
it's the best tool we have for privacy. I mean, it's truly amazing, you know, the researchers and the work that's been put into this. And, you know, I really hope that we get private governance, that we get private balance transfers, that we get really proper privacy in the Polkadot network over time.
Yeah,
so
totally.
We'll need ZK.
Rob, thank you for coming on the show and stopping in and explaining your exciting work. We look forward to seeing what you have to say next time you're on.
Thank you.